Welcome to this deep dive into one of the most influential papers in the history of artificial intelligence. Published in 2017 by researchers at Google, Attention is All You Need introduced the transformer architecture. This architecture is the foundation of virtually every modern AI language model, including GPT, Claude, BERT, and countless others. To appreciate what the transformer achieved, we need to understand what existed before it. In 2017, AI relied on recurrent neural networks, particularly LSTMs and GRUs, for sequence processing tasks like machine translation. These process sequences one element at a time, left to right, maintaining a hidden state that carried information forward. This approach had three critical problems. Sequential processing was slow, long-range dependencies were hard, and the gradient problem. Because each step depended on the previous, computation could not be parallelized, making training extremely slow. RNNs struggled with long-range dependencies, as information tended to degrade over many steps. The authors proposed something radical. What if we got rid of recurrence entirely? What if we processed all positions simultaneously and let each position directly attend to every other position? This is the core insight of the transformer. Attention is all you need. Attention mechanisms existed before the transformer, but let's understand what attention actually means. Think about how you read a document. When you encounter a pronoun like it, your brain immediately looks back to find what it refers to. That's what attention does in neural networks. It allows the model to look at all positions in a sequence and decide which are most relevant. The transformer uses scaled dot product attention with three concepts: queries, keys, and values. Imagine you're at a library. You have a query, a question. Books have keys, titles, and values, the actual information. You compare your query against all keys to find matches, then combine the values based on relevance. Mathematically, the attention mechanism is elegant. Attention, softmax XV. First, QKNT computes the dot product between each query and all keys, giving a compatibility score. Then, divide by the square root of the key dimension, dk, for scaling. This prevents large dot products from pushing softmax into regions with near-zero gradients. Finally, softmax converts scores into probabilities, and these weights are multiplied by the values to compute a weighted sum. Here's the crucial insight. In the transformer, queries, keys, and values all come from the same sequence. This is called self-attention. When processing a sentence, each word creates a query, key, and value, then attends to all words to determine relevance. The word sat might strongly attend to cat and mat, learning these relationships automatically. And here's the magic, all of this happens in parallel. Unlike RNNs, self-attention computes all attention weights simultaneously using matrix multiplication, leading to massively faster training. The authors didn't stop at single attention. They introduced multi-head attention. Different aspects of language require different types of attention, like syntactic, semantic, or positional relationships. Multi-head attention solves this by running multiple attention operations in parallel, each called a head. Each head has its own learned projection matrices, transforming queries, keys, and values into different subspaces. The outputs from all heads are then concatenated and projected back to the original dimension. Research showed that different attention heads indeed specialize. Some focus on nearby words, some on syntactic relationships, and others on semantic patterns. The transformer is designed for sequence-to-sequence tasks like machine translation, with an encoder and a decoder. The encoder processes the input sequence and builds a rich representation, while the decoder generates the output sequence. The encoder consists of n or 6 identical layers, each with multi-head self-attention and a feed-forward network. The decoder also has 6 identical layers, but with 3 sublayers: masked multi-head self-attention, multi-head cross-attention, and a feed-forward network. Masking in the decoder is crucial. It prevents the model from cheating by looking at future positions during training. The transformer has no inherent notion of position, but word order matters enormously in language. The solution: positional encodings. These add a position-dependent signal to each token embedding using sinusoidal functions. This creates a unique fingerprint for each position, helping the model generalize to longer sequences. The transformer didn't just achieve state-of-the-art results, it enabled an entirely new paradigm in AI. In 2018, BERT revolutionized NLP, achieving state-of-the-art on 11 different tasks. GPT and GPT-2 showed that scaling up produced increasingly capable models, leading to GPT-3 with 175 billion parameters. This culminated in the explosion of capable AI assistants like ChatGPT, Claude, and GPT-4, all built on Transformer foundations. The Transformer's parallelizability was the key to everything that followed, enabling the scaling laws that drive modern AI. The deepest insight of the paper is in its title, Attention is All You Need. The authors showed that complex recurrence and convolution were not necessary for state-of-the-art sequence modeling. Pure attention, applied correctly, was sufficient. This simplification is the hallmark of truly important research. The 8 researchers who wrote this paper in 2017 couldn't have known they were laying the foundation for an AI revolution. But by asking a simple question, what if attention is all we need? They discovered an architecture that was simpler, faster, and more powerful.